Good afternoon once again. We are meeting on a different topic. It's Nozzles by Steam for Power Machines N6 Activity 5.2 for those who are still using the book by Hegner in Detroit. Now the question says steam enters a group of convergent divergent nozzles at a pressure of 2 megapascal and a temperature of 250 degrees Celsius. The velocity of dry saturated steam at the throat is 498 meters per second, and the diameter of the throat is 66.5 millimeters. Expansion through the nozzle takes place to an exit pressure of 380 kilopascal. The flow is frictionless and adiabatic up to the throat. The efficiency from the throat to the exit is 90%. At the exit, the isentropic drainage factor of steam is 0.93. Ignore the velocity of steam at inlet. Use only steam tables to answer the questions. So the first part, the specific enthalpy of steam at the throat, and then use the steam tables to determine the pressure, the temperature, and the volume at the throat. So on the first question, we are challenged to find the specific enthalpy of steam at the throat, which is our HC. So, but first and foremost, the first important thing that we need to do on our A is to find our H1. H1, which is our HSU. So how do we get our HSU? We are given a pressure of 2000 kilopascal and a pressure of 250. So we can go to our superheated steam table. You look for a 2000 kilopascal where they are intersecting at HSU. I'm getting 2905. So our HSU is 2904 kilojoules per kg at 2000 kilopascal and 250 degrees Celsius. So we now have our H1. Now we can use now our formula for CC, which says CC equals to square root of 2000 times or into H1 minus our HC. Yeah, we can use this one. It has to work. So let's check what are we having there. Are we given our CC? We are given the throat velocity of 498. So our throat velocity is 498 meters per second to the square root of 2000 into, we got our H1, which is 2904 minus our HC. So from here, we make our HC a subject of the formula. So if you get our HC there, we are going to say 2908. Rather, we can say 498 divided by 2000 minus 2904, but you must not forget we have square root, so it becomes 498 squared. So I'm getting something like HC2 780 kilojoules per kg. So we are getting our HC as 2780. So 2780. So from there we go to our steam table because they said calculate the specific enthalpy of steam at the throat. So we found out that our HC at the throat is 2780. So you need to rush on the steam table, and then to find the pressure, we need to get our PC as well as our temperature and our volume at the throat. So you need to look for 2798 on the normal steam table. So you need to make sure that in the exam, you open your eyes and you move very fast. You move very fast. We're looking for 2780. So if you check on our steam table, what are we looking for there? We are looking for HC, but on our steam table, we don't have HC. Therefore, you must remember HG equals to SC. So we are looking for HG at 2780 kilojoules. So that's what we are looking for. So if you look there, I'm finding 2780, the pressure. My PC, I'm finding it at 2780. I'm finding it to be 1100 kilopascal. So that's my PG, my PC, and then my TC. Remember, they want us to get the temperature, the pressure, as well as our VC. So TC at 2780 kilojoules per kg. You go to 1.1, I'm getting my TC is 184.1. I'm getting 184.1 degrees Celsius. And we also need our VC. But VC in this case equals to VG at 2780 kilojoules per kg. Because we cannot use our formula. In this case, VC equals to 0.231 into HC minus 1941 over our PC. Because in this context, our N was not given. So in that regard, if our N is not given, just go to your HG at 2780, you get your VC. Your VC is equal to your VG. So I'm seeing at 1.1, my VG is equal to 0.1774 meter cubed per kg. So we are done. On our A, we have our H1, we have our HC, we have our PC, we have our TC, and we have our VC. So our throat conditions for A, we are sorted. And then on number B, the question says calculate the area at the throat and the mass flow rate of steam in kgs per second. Now, if we check here, earlier on, we are given our throat diameter. So it's a simple one. We can use our formula AC equals to pi DC squared over 4. We can use this simple formula, which is pi. Since they specified, or they didn't specify whether we need to calculate the area in cubic meters, so we can leave it in millimeters the way it is. 66.5 squared over 4. So let's see what are we getting as our area, which is bracket 66.5 bracket squared over 4, which is I'm getting 3473.227 millimeter squared. So if they wanted this one in meter squared, we simply times 10 to the exponent of negative 6. So if you want to change it to meter squared, you times by 10 to the power of negative 6, which becomes 3.473 meter squared. So we have our area. After getting our area, they also want us to calculate the mass flow rate. So they want us to calculate our mass flow rate, but our formula says AC equals to MVC over our CC. What are we having there? So they want us to calculate the mass flow rate. AC, we have it. And they emphasized air in kgs, the area as well as the mass flow rate in kgs per second. So our AC is 3.473. We are looking for our mass flow rate, VC. We said our VC is 0.1774. Our CC, it was given as 498. So from there we make our M a subject of the formula. So we look for our M, which becomes 3.473 times 498 all divided by 0.1774. Oh, don't forget, we didn't do something right on our area there. We have 473.227 times 10 to the power of negative 6. So our answer is not, it is having an exponent times 10 raised to the power of negative 3 meter squared. So here we also substitute times 10 to the power of negative 3, which becomes 3.473 times 10 raised to the power of negative 3 equals to M times 0.1774 over 498. Let's get our mass, which is proper now. So we have 3.47 times 10 raised to the power of negative 3 times 498 divided by 0.1774. I'm getting 9.741 kgs per second. Yeah, so you can see the answer. It communicates with you that because when I forgot to put the negative 3 here, my answer became, for the mass, it was a bit abnormal. So you can see now that you are relevant. Now let's go to number C. A and B, we are done. On number C, they want us to calculate the isentropic enthalpy and the actual enthalpy at exit. So they want us to calculate our H2 prime equals to HF plus Q prime times our HFG. So we are saying H2 prime equals to HF plus Q prime times our HFG. At exit pressure, our exit pressure, it was said to an exit pressure of 380. So at 380 kilopascal. So we got our steam table at 380. Where is our 380? So our HF is 597 plus was our actual drainage factor, isentropic drainage factor given. Our isentropic drainage factor, yes, it was given as 0.93 times. Let's look for our HFG. HFG at 380 is 2139. 2139. So let's get our answer. So we have 597 plus bracket 0.93 times 2139. I'm getting 2586.27 kilojoules per kg. I hope it's clear and I hope we are following. Now, we need to get also the actual. So, but actual enthalpy, which is our H2, equals to HF plus Q2 times our HFG at 380 kilopascal. So the conditions for getting our actual and the isentropic are the same because the pressure is still the same. But we just have one small problem. You can see that the actual drainage factor was not given, but we were given the efficiency from the throat to the exit as 90%. So we can use that formula which says efficiency in the divergent part equals to HC minus H2 over HC minus our H2 prime. So we can use this one. We have our efficiency, we have our H2 prime, we have our HC. So it's easy for us to get our H2 actual. So these are our H2 actual. That's what we are looking for. Efficiency, it was given as 90%. We divide by 100 because remember this is times 100%. It's efficiency. So if we divide by 100, we are getting 0.9 equals to, let me change my pen here. So it's 0.9 equals to our HC. We got our HC as 2780 minus our H2 over our HC, which is 2780 minus H2 prime. We got it as 2586.27. So from there, let us make our H2 actual the subject of the formula. So if we substitute there, we have, let me see what are we getting. Okay, times 2780. So I'm getting 2605 64 kilojoules per kg. So we now have our actual enthalpy. So we have our actual enthalpy and we have our isentropic. We can now easily go to number D. The one, the velocity in meters per second, actual drainage factor of steam, volume in cubic meters per kg, and the actual area at the exit. So they want conditions at the exit. They want conditions at the exit. So that's our number D. So we can start by saying C2 equals to square root of 2000 into H1 minus our H2. So which becomes square root of 2000, our H1 we say 2904, H2 we just got it now, which is 2605.64. So let's see what are we getting there. Let me punch. So I'm getting my C 277 2.477 meters per second. So we have our velocity and then we need our actual drainage factor. So to get our actual drainage factor, but H2 equals to HF plus Q2 times our HFG at 380 kilopascal. So it is taking us back to this formula. So our H2, we said, is 2605.64 equals to our HF at 380. We already got it, which is 597 plus our Q2 actual. Our HFG, we got it as 2139. So there, let's get our actual drainage factor. let's get our actual dryness factor, which is 2605.64 minus 597 all divided by 2139. So we have 2605.64 minus 597 all divided by 2139. I'm getting 0.94. So our actual dryness factor is 0.94. So we'll write part of our B on this other side because we are running out of space there. So we also need to get the volume in cubic meters per kg. So we need to get our V2, but V2 equals to Q2 times our VG at 380 kilopascal. We got our Q2 as 0.92. That's our dryness factor, 0.92 times. We need to get our VG at 380. Okay, VG at 380 is 0.4851. 0.4851. So let's see what are we getting. 0.92 times 0.4851. I'm getting 0.446 meter cubed per kg. So what is remaining now? They also want the area at the exit. So we want our A2, but A2 equals to MV2 over our C2. Our mass, we got it as 9.74. Our V2, 0.446. Yes, 0.446, all divided by our C2, which is 2.477. So let's get our mass. Okay, which is 9.74 times 0.446, all divided by 772.477. So I'm getting 5.623 times 10 to the power of negative 3 meter squared. So that's how you approach a question like this. That's how you approach a question like this. You must also remember how to calculate your mesh number. So how to calculate your mesh number. I think as I'm going to introduce my second lesson, I'll try to write a number of formulas and the conditions that we need to adhere to when we are dealing with nozzles by steam. Yeah, so when we meet on our second lesson, I'll introduce that part. I'll be specifically dealing on the diagram of steam nozzles and the conditions at which we need to remember. Thank you, until we meet on the other lesson. Sharp guys.